That's the quintessential example. Now, it's exactly the same reaction I showed you for SN1, only now I have drawn in an alkene, not an epoxide. That's the difference. Let's take a look. So now to do the reaction mechanism, the first step, we all know it. The leaving group leaves. So literally, we're talking about the same mechanism in the first step. Now I drew out that top methyl group for a reason. So now in SN1, the oxygen from the solvent would have attacked this carbon. Now I'm going to say the oxygen from the solvent is going to attack that hydrogen. Now you may be wondering why it would do that. And now in this previous part of this unit, we talked about induction. We said, okay, and I said it was going to become important after a while. We talked about hyperconjugation and induction on the same slide. Oops, not delta positive. And we said, okay, this is going to pull electron density from here, 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 and from there, and from there, from there, from there. And I said that all of these protons, or all these hydrogens, are delta positive, right? And indeed they are. From induction, they're all delta positive, slight positive charges on all of these hydrogens. Well, if you show a delta negative to anything that's positive or delta positive, they're going to be attracted to each other. So these hydrogens are delta positive from induction. This oxygen is delta negative from polarizing because of induction. It's similar, right? It's more electronegative, induction, delta negative. So now these electrons will be attracted to that hydrogen. They'll attack it, deprotonate it essentially. The electrons from that bond will go down here to form a pi bond with that carbon. And that's actually step 2. I should have drawn it down here. Sorry, let me draw it down here for completion's sake. Sorry about that, guys. You get to see it twice. You get to see the mechanism twice. All right, so delta positive here on that hydrogen. Here comes the solvent. Solvent is delta negative at oxygen. So now the lone pair from the O will attack the hydrogen. If we stop there, we break in the duet rule, or hydrogen will have too many electrons. So these electrons from this bond must go down here to form the pi bond. So that's what's occurring. And there you go. That's how the reaction works. So up to here, it's the same as an SN1 reaction. SN1 would have attacked here. E1 attacks the protons. And that's the difference. That's the only difference. Only difference is what happens. Does the oxygen of the solvent behave as a nucleophile and attack the carbon? Or does it behave as a base and attack the hydrogen? It will do both. Given the opportunity, it will do both. You have to remember, molecules and atoms and ions are not thinking. They're reacting to the attractive forces around them. Here's the energy diagram. Same idea as the SN1. It's a 2-hump reaction. The first step is rate limiting because the first step forms the carbocation. Transition states, very similar. So the transition state will be, for the first step, that's the mechanism, that's the first step. So then the transition state will look something like this. Oops. So that's transition state 1, where the halide is leaving. Transition state 2 will look more like this. It'll be and I guess here we're calling it the base. There we go. That'll be transition state 2. As the pi bond is forming and the bond to hydrogen to carbon is breaking, and the bond to base and hydrogen is forming. Again, first order reaction. First step is rate limiting. The only thing that's in the transition state for the first step is the alkyl halide. The bond is breaking. That's the first step. The second step is faster. It's not rate limiting. So it's just the deprotonation using the base, take off the hydrogen to form the pi bond. All right, so now that we've learned about SN1 reactions, E1 reactions, deprotonation, double bond formation, all this kind of stuff, we need to learn about something called Zaitsev's rule. Now, Zaitsev's rule says, all things being equal, given a choice, a more substituted double bond will be the major product. A more substituted double bond will be the major product in an E1 reaction, all things being equal. So let's take a look at bonding patterns. So here is a mono-substituted double bond. It has one alkyl group on the double bond. The rest are hydrogens. Okay, let's see a di-substituted. So in a reaction, given the choice, the more substituted double bond will form in an E1 reaction and in an E2. We're going to get to E2s also. In E1 and E2 reactions, the more, all things being equal, the more substituted double bond will form. Now, obviously, we can make things unequal to go the way we want, but left to their own devices, the more substituted double bond will form. So, we're drawing a mono-substituted right here, di-substituted, tri-substituted, and tetra-substituted. All things being equal, the more substituted double bond is the one that forms. And that's Zaitsev's rule. That's Zaitsev's rule. So when doing E1 reactions, remember, the more abundant alkene will be the one that is more substituted. Zaitsev's rule states, if more than one elimination product is possible, the most substituted alkane is the major product. It's also the most stable. That's Zaitsev's rule, stated out nicely for you. Now, the E1 reaction and the SN1 reaction, as I said before, are competing with each other. So let's see an example of that. Let's imagine then we have a and methanol. Now, let's just predict some products that could occur. Now, I'm not saying any of these will occur. Some of them likely will. Maybe not all of them. Let's just see. Let's predict some products. What could this molecule do? Well, it's in a polar protic solvent, and it's a tertiary halide, so SN1, E1 all day long. SN1, E1 all day long. So, draw the carbocation. Now it's tertiary, so more than likely there'll be no rearrangements because it's already tertiary. First thing that can happen is the solvent can attack SN1 style, right? Solvent can attack SN1 style. And of course, the solvent will deprotonate it for us. Oops. And one of the products potentially could be the ether. More than likely you'll get the ether product as one of the products in this reaction. There. No question about it. No question, you'll probably get some at least SN1 product. But you can also get the E1 products, right? Now, this is an interesting case because there's two potential products. Notice how I'm redrawing my carbocation. I am not doing three or four different mechanisms on the same carbocation. Things just get really confusing. So now here, this cation is symmetrical through here. There's a plane of symmetry through here. So these hydrogens here and these hydrogens here are the same. So if I deprotonate here or I deprotonate here, I'm going to get the same product because of the symmetry of the molecule. So just do one. There's one of the potential products you can get from the E1 reaction. There you go. That's one potential. No problem there. But now don't forget, there's hydrogens on here too, right? There's hydrogens on that methyl group. So let's draw that. Here we go. Into there. And that will give us that alkene. So there's three potential products from one reaction. Now between these two, you can easily predict that this is the more abundant product. How can I say that? This is the Zaitsev product. It is 1, 2, 3 tertiary or tri-substituted, it's a tri-substituted alkene. This is a di-substituted alkene. Tertiary, according to Zaitsev's rule, should form in predominance. So that should be the predominant alkene at least. Now, will it be more abundant than the SN1 product? Difficult to say. All right, so that's how you do that. Now remember, a carbocation can do a lot of things. Carbocation can form an alkene, E1, can form an ether, SN1, can also rearrange. And once it rearranges, it can do all the same reactions again. So if you go from one carbocation to a different carbocation, the original carbocation could react, E1, SN1 style, before it rearranges. The rearrangement may be slow. Keep that in mind. So if you have two different carbocations forming in a reaction, you can have E1 and SN1 for both carbocations. Okay? So carbocations can do a lot of things.